Problem 4.133. The couple M is applied to a beam of the cross-section shown in a plane forming an angle beta with the vertical. Determine the stress at point A, point B, and point D. So I did this problem earlier. I thought I had it, and then I realized I made a bunch of little mistakes, but I learned a lot from it. So I will tell them to you as we go through the problem so that you don't make the same mistakes, because it's frustrating. All right. So let's look at the right figure. We've already done the left one. The left one's a little bit easier. The right one has some nuances that you have to take into account. So the first thing you want to do when you have this type of unsymmetric bending, because the moment vector is not aligned with one of the principal axes of this cross-sectional area for this beam, is 1, find the principal axes. Here they gave them to us, Z and Y, so we don't have to worry about those. And then find the moments of area about the Y and Z axes, which are the principal axes. All right, so let's do that. So let's focus on I, Y. If you go on your equation sheet, you'll see that for I, Y, you're going to find that the formula is 1/8 pi r to the 4th. So that's 1/8 pi and 20 millimeters to the 4th. We'll put that into the calculator later. Now, here's the question. On the equation sheet, you have the formula for the axis around this axis, for the moment of inertia around this. So you'll have to shift this by this amount using the parallel axis theorem, which is what I was doing earlier. But are you going to add or subtract? Well, it turns out, if you think about it, if you're going here, then the overall distance of the whole mass from the axis is less. So you're going to have to subtract, not add it, right? And so that's the mistake. That's the first mistake I made. So let's not make that mistake. And let's think about the parallel axis theorem for a second. IZ is going to be what? Well, we have 1/8 pi r4, that's from the AD point, and then we need to shift it. We're going to have to subtract, we just talked about that. We're going to have to subtract the total area of this, which is what? It's a semicircle, so that's going to be pi r squared over 2. And that's our area, and then our distance, which is this distance over here. Now, how do we find that distance over here? We'll call that distance y. So to find y, and we're gonna have to find that first. There is another. That's the point where the centroid is. So if you go to the page of the centroid for that shape, and make sure it's the semicircular area, not the semicircular arc, because the semicircular area has mass within its area. We see that the formula, it's the second row on the second column, is 4r over 3 pi. So 4r over 3 pi is what we will have to shift it by, and that's the distance, and it has to be squared. So let's do some algebra to rearrange that. Over 3 pi, we might need this later, so we'll just do it here as well. So we have 4 times 20 millimeters over 3 times pi. So let me put that into the calculator. 4 times 20 divided by 3 times pi. What we're going to get is 8.488. All right. So 8.488 millimeters. along the y-axis. Now, that's just the distance. That's just the distance. I don't want you to think that it's from a particular axis because it's in the, it's actually, see, it's in the negative y direction. Well, it's going up towards the positive, but it's the y direction starts to be negative here. So it's just that distance. Now, let's think about what we're going to do over here. Well, here we're going to have 1/8 pi times 20 millimeters to the fourth minus pi times another 20 millimeters to the, no, that's squared. That's the area. Divided by 2, remember that's a semicircle, multiplied by what we just found, squared. So let's plug that in. We could do some algebra and make it simpler, but let's just plug that in. We don't want to make careless mistakes, and then they don't train you to do too much algebra. They just want you to understand the concepts. So pi times 20 squared divided by 2 times 8.488 squared. So let me just check that I inputted everything correctly. 1/8 pi times 20 millimeters to the fourth minus pi times 20 squared divided by 2 times 8.488 squared. We plug that in, and what we get is 1.7564 times 10 to the 4 millimeters to the fourth. Okay, let's do the top one while we're at it. Times pi times 20 to the fourth. I don't know, I did something weird with the calculator. Let me back off. Times 20 to the fourth. And we get 6.2832. 6.2832 millimeters to the fourth. So that was the first big mistake I made. I forgot to subtract while I didn't realize what I was doing. I just did not have a full understanding. Now, once we do that, we go to part 2. What is part 2? Decompose the moment vector along the z and y axis, the z and y axis, which are the principal axes. And I wanted to put plural here. All right, so let's look over here. We're going to decompose this like this. And remember, this is not a vector for a force. So the thumb points in that direction, the fingers curl in this direction, and so that's the overall moment. The fingers are going to curl like this and like this because, and this is another thing important, think about your eye looking straight down, it's going to see a counterclockwise moment. So when your eye moves to looking straight down here, it still wants to see a counterclockwise moment, and the same applies to here. This is just something that you need to understand in order to get the signs right. So what we're going to do is we're going to say, hey, this is also 30 degrees. So I can decompose this in m cosine 30 degrees and this one in m sine 30 degrees. So let's do that. And so the one that is parallel to the y-axis, we'll call it my. My is going to be m sine of 30 degrees, which is equal to 100 divided by 2, which is 50 Newton meters. And mz is going to be m cosine of 30 degrees, which is still going to be 50, but now I'm going to have to multiply by the square root of 3, and we get 86.6 Newton meters. All right, so we did step 2. Step 3, what is step 3? Find the distances of the points of interest. So we said, and we're going to have to find a distance with respect, so distances from the y-axis and distances from the z-axis, because we have moments about both of these axes. So I'm going to ask you a question. How far is A from the z-axis? Well, that y distance that we found earlier, 8.488. So YA is 8.488 millimeters. How about from the z-axis? How far is A from the z-axis? Well, look, the z-axis is right here. This is the second mistake I made. I was thinking, oh, the z-axis is there. No, the z-axis is right there. It's depicted. What is this distance? Well, it's again y, and it's in the negative y direction. So I meant to say that we are far away from the z-axis, a y distance of 8.44. That's that distance. And now I want to know the distance along the z-axis. So along the z-axis, A is this distance. That's the radius. So that is 20 millimeters. Okay? Well, what about B? YB, distance along y. So the y coordinate of B. Well, that's going to be the radius minus my distance y with that little line on the top, right? So that's going to be the radius minus this, which is going to be 20 millimeters minus 8.488 millimeters. And then finally, we're going to have, not finally, we got more. So ZB, what is my Z coordinate? Well, it's 0. But what about, okay, let's do that, minus 8.488. That's going to be 11.5. 11.5 millimeters. What about y of the point D, the y coordinate of the point D? Well, the point D is at negative that y distance, so it's at negative 8.488 millimeters. And the Z for point D is negative the radius, so negative 20 millimeters. So those were the two big mistakes I made. I didn't realize that the z-axis is not the bottom of our figure, and I didn't realize that we had to subtract the moment here. So now what I'm going to do, number 4, is apply superposition. So applying superposition, we're going to get that the stress along the x-axis is going to be equal to, and I like to reason the signs here. So let's think about it. If I get a moment as depicted just around the z-axis, I'm going to get compression on the top. So I'm going to get compression here. So compression means I want a negative sign. And my y distance, though, is positive. So I'll need to have a negative in front. So that's going to be negative mzy over iz. That doesn't happen for the y. And I'll show you why. No pun intended. If you look at y, then if we have a positive moment that looks like this, we're going to have what? We're going to have tension here, tension. Well, that means that if I go in the positive z direction, I want a positive sign, so I don't need to change the sign. So that's why it's positive. And so then we do apply the formula for the different parts. So I'll just make the first one, and then I'll use the power of copy and paste. So for mz, we have 86.6. 86.6. Convert this to kilonewton millimeters. Trust me, that's going to give us megapascals at the end. Let me make this a little bit bigger for you guys. Minus 86.6 kilonewton millimeters. Our y, we decided, is 8.488 millimeters for A. Now, this is where we have to be careful. we are going down. We are going down the y-axis. So that's negative. So that's going to be, so that's my bad. See, they're full of mistakes, full of potential mistakes. Minus 8.488 millimeters divided by IZ, which is 1.7564. 1.7564 times 10 to the 4 millimeters to the fourth, plus we have my, which is 50 Newton meters, which we convert to 50 kilonewtons times millimeters. And then we have our ZA, which is 20 millimeters. And that's good because A is on the left. Look, A is on the left. Z is positive on the left, so that's positive. I just don't want to mess that up. And then we have IY, 6.2832. I forgot it, times 10 to the 4 millimeters squared. 6.2832 times 10 to the 4. To the fourth. See, I kind of knew because I was like, hey, this is huge. Why is this one so small? And so I figured I was missing something. So now what I'm going to do is I'm going to take this and I'm going to copy it. And I'm going to paste here. And paste it one more time here. And this is going to be my B and D. So B, D. So some things are going to change. My YB is going to be positive 11.5 and 0. Positive 11.5, and this is just going to be 0. My D is going to be minus 8.488 and minus 20. So both of these, this is going to become negative. And so doing all of this is a drum roll moment. You put it into the calculator and you really hope you got it right, because if you didn't, let me tell you, it's frustrating, especially after doing all this work. But you always learn from it. Minus 8.488 divided by 1.7564 times 10 to the fourth. So we've done that part. Now I'm going to add 50 000 times 20 divided by 6.2832. 6.2832 times 10 to the fourth, right? So now we have 57.8, we'll say. 57.8 megapascals. And it is positive, so this is in tension. All right. That's in tension. Now we could do the same. We just have to change a couple things. We have a 0 on the second term, so that whole thing goes to 0. And the first term has a y of positive 11.5. So that gives us minus 56.7. So that's compression, megapascals. And then the last one is going to be with a negative 20. And then everything else is the same. So that's going to be 25.9. 25.9 megapascals in tension. And so these are our stresses at the points requested. And hopefully, those are correct. And I'm just seeing now the answers. Yes, they are. Oof. I hope this was useful. This is how to do unsymmetric bending. Good luck on anything else you're going to do. Have a good day.